Hello, let's talk about quantum numbers. And what these numbers are answers, if you will, that are derived from the quantum mechanical wave equations, Schrodinger's equations for the hydrogen atom. We're not going to care what those equations are. We just want to care about what the solutions are to them in essence. And so there are going to be four quantum numbers that we want to talk about. The first one is a principal quantum number. And we're going to denote that with a lowercase n. And it determines the size of the orbital and the energy of the orbital. The greater the value of n, the greater the size of the orbital, and the greater the energy of the associated electrons in that orbital. Principal quantum number has to be an integer that's greater than 0. So it can be 1, 2, 3, 4, etc. So that's the principal quantum number. The second quantum number that we want to talk about is the angular momentum quantum number. That we're going to designate, call L. L has integer values from 0 up to n minus 1. From 0 to n minus 1. The other thing about L is we also want to have some associated letter designations to this, or as we talk about atomic orbitals. So if we have L values of 0, 1, 2, or 3, the letter designations are going to be S, P, D, and F. So if you've got a L value of 0, it can be referred to as an S orbital. L value of 1, it'll be a P orbital. L value of 2 would be a D orbital. And an L value of 3 would be an F orbital. And so those you need to remember. The next quantum number is the magnetic quantum number. M subscript L, or M sub L is how we would pronounce that. And it's going to have integer values that range from minus L to 0 to plus L. And once again, these are falling out of those Schrodinger equations for the hydrogen atom. So for example, rolling all three of these quantum numbers together at the moment. When n is 1, the only possible value for L is 0 because it goes from 0 to n minus 1. And the only possible value for m sub L, which goes from minus L to 0 to plus L, would also be 0. So that's for the case n equals 1. If n equals 2, L can have two values, 0 or 1, and those would respectively refer to S or P orbitals. I can go back and put an S for the n equal 1, L equals 0 value. Then the associated or corresponding m sub L values, L is 0, the only value for m sub l is 0. If L is 1, m sub l can be -1, 0, or +1. If n equals 3, the L values can be 0, 1, or 2, because we can only go up to n minus 1. Corresponding letter designations would be S, P, or D. And so if L is 0, the only possible value for m sub l is 0. If L is 1, the values are -1, 0, and +1. If L is 2, possible values are -2, -1, 0, +1, and +2. Let's go one step further. What if we get up to it where n equals 4? Now there are 4 possible values for m sub l of 0, 1, 2, or 3. Can't be 4 because it has to be at least one integer value less than whatever n is. So if n is 4, the greatest value for L would be 3. These correspond to S, P, D, and F. If L equals 0, if it's an s orbital, there's only that single s orbital available. There's only one value for m sub l. For P, -1, 0, +1. Because we're going from -L to +L. If L is equal to 2, -2, -1, 0, +1, +2, and +3 are the possible values for m sub l. If L is equal to 3, now we're up to an f orbital. -3, -2, -1, 0, 1, 2, and 3 are the possible values for m sub l. So these orbitals are going to be these three-dimensional shapes that we're going to carve out in space, if you will, that will show us the probability of finding an electron. So an orbital can hold a maximum of 2 electrons. So if we went back through this, the max number of electrons for n equal 1, L equals 0, m sub l equals 0, there's one orbital, each can hold 2 electrons, maximum number is 2. For n equals 2, for the s orbital, there's a maximum of 2 electrons. For p orbitals, there's a maximum of 6 electrons. 3 orbitals, the -1, 0, +1 m sub l values, each can hold 2 electrons, gives us 6. So for n equals 3, 0, 6. For L equals 0 and L equals 1 respectively, those are the maximum number of electrons. If L equals 2, we've got 1, 2, 3, 4, 5 orbitals. Each can hold 2 electrons, or a maximum of 10 electrons. For n equals 4, if it's an s orbital, it can only hold 2 electrons. For the set of p orbitals, there are 3 of them, with m sub l values of -1, 0, and +1. That would give us a maximum of 6 electrons. If we're up to n equals 4, we can have d orbitals, and there's 5 of those that correspond to the m sub l values of -2, 0, 1, +1, +2. Oops, got a mistake there. Got a little carried away. So there are 5 orbitals, or a maximum of 10 electrons. And then for the f orbitals, there are 1, 2, 3, 4, 5, 6, 7 orbitals available. Each can hold a maximum of 2 electrons. That would be 14 electrons. So those are the first 3 quantum numbers. There were 4 quantum numbers. And the last one is the spin quantum number, or m sub s. And this is where we're going to see how we can have 2 electrons in each of those orbitals. And the spins are either going to be designated as +0.5 or -0.5. That's the spin quantum number, m sub s. So to summarize, we can designate an orbital in an atom with a set of 3 quantum numbers. And to designate all the electrons in an orbital, we need that 4th quantum number, m sub s, that designates the spin.